Okay, hi everyone. So diagonalizable operators. So a diagonal matrix is something like this, which just has zeros everywhere, except on this part, which is called the diagonal. So this one is A11, this one is A22, this one is A33, entry in row 3, column 3 is non-zero, but anything like A12, which would be this thing, has to be 0. So an operator is called diagonalizable when there is a basis such that if you write its matrix in that basis, you get a diagonal matrix. Okay. If you choose a different basis, then the matrix will probably not be diagonal, right? So you have to choose a very special basis, a basis of eigenvectors, in order to make the matrix diagonal. Sometimes this is possible, sometimes it's not. It's exactly possible when the minimal polynomial of t factors into linear factors with no repeated factors. So like x minus 2 and x minus 2 would be bad. You can't have it happen twice. You can't have it squared. You can have an x minus 3, you can have an x minus pi, whatever you want. You just can't have them happen twice. You can't have an x squared plus something like a quadratic term. That would be bad too. Then you're not diagonalizable over the reals. Okay. So what's the precise definition of an eigenspace? Your book's notation is this. It's just, there's two, maybe one definition is it's the null space of t minus lambda times the identity. So this operator has come up many times, both the range of it and the null space of it, many times in proof. So we've seen it before. And if a vector is in the null space of this operator, that means that t minus lambda times the identity v is 0. But that means tv minus lambda v is 0. But that means tv is lambda v. And so, the null space consists of eigenvectors and also the 0 vector, which is not an eigenvector but would still satisfy this requirement. So another way to say this is that the eigenspace is equal to the set of all eigenvectors, which is in fact a subspace because it's the null space of an operator, and it's a subspace, along with the 0 vector, which is not an eigenvector. Eigenvectors have to be non-zero. But, the 0 vector is in the null space here, and so we're going to throw it into this thing so that this thing is a subspace. Okay. Describe T restricted to the lambda eigenspace. Well, if we only feed, so what does it mean to restrict? It means we only feed T elements of this subspace rather than feeding T elements of the whole vector space. And so if we only feed things in this subspace, well then T on that thing will always be lambda v. Okay, even if we feed T the 0 vector, that's still lambda times the 0 vector. So it just works. So T restricted to it, choose a basis of the subspace. Every basis element will be an eigenvector, and so the matrix of T restricted to E lambda T would be a diagonal matrix with lambda on the diagonal, however many times to make up the dimension of this subspace. If this has dimension 4, then there'd be 4 lambdas, and it'd be a 4 by 4 matrix. And T restricted here, it just scales everything by lambda. So you could say it's equal to lambda times the identity, because this thing just scales every vector by lambda. Okay. So let's do this number 5. Let's actually prove it. Let T be an operator, and let these lambdas be distinct eigenvalues. Okay. Show that the sum. So these are subspaces, and we're gonna add them up. Show that it's a direct sum. Okay, so remember we had many different, 3 different equivalent ways to show that something is a direct sum. One of the ways is to show that, okay, so what's the definition of the sum? So let's see. Okay, how do we show this is a direct sum? u1 plus u2 plus dot 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 plus um equal the zero vector, where each ui is from the lambda I eigenspace. Okay, so the sum of subspaces is just the collection of all sums like this, where each term in the sum is in the corresponding subspace. So u2 would be in e lambda 2, u1 would be some vector in e lambda 1, etc. So when we have this, so let this be true, okay? One of the ways we can show that something is a direct sum, to show, let's call this thing star, the sum of subspaces star, to show star is direct, we need to show, so one of the equivalent ways is to show that the only way this happens is if every vector here is the zero vector. And that was, we proved that a long time ago, that it's equivalent to the sum being direct. We need to show each ui is actually the zero vector. Now, each of these subspaces is a subspace. It has the zero vector in it. So it's possible that these are all the zero vector, but the key is we're just letting this be zero, and possibly non-zero vectors in here that sort of cancel each other to zero. But we're going to show that can't happen. Since each ui is an eigenvector. Why is it an eigenvector? Because it comes from this subspace, and the set of this subspace is all the eigenvectors. Is an eigenvector, or zero. It could be the zero vector, but they're eigenvectors or zero, so they're either zero or they're eigenvectors with distinct eigenvalues. Then we show that they're independent. They are independent. But that means that if we have any linear combination of them equaling to zero, all the coefficients have to be zero. Well, hold on a second. This is a linear combination where all the coefficients are 1. So the coefficients are 1, they can't be 0. So what's the way out of this? Well, we have a linear combination which is 0, and the coefficients can't be 0. So what's the only way that can happen for independent vectors? Well, it can't happen for independent vectors. They are independent, comma, unless they are all the zero vector. They are all the zero vector. Right? Because if only one of them was the zero vector, then we'd have the similar problem, that we'd have a linear combination with non-zero coefficients giving the zero vector of the others. So then that can't be true, because these are independent. If these are non-zero eigenvectors, then they're independent. So this can't be. So that means that one of them has to be 0, and we keep going, and they're all 0. So that ends the proof. We've showed that each of them is 0. Okay. Good. So let's look here. So this is a big proof, but lots of it are very simple. For example, so if these are distinct eigenvalues, if T is diagonalizable, if A holds, can we show that A implies B? Yeah, because if it's diagonalizable, that means there is a basis where the matrix is a diagonal matrix, but then that basis consists of eigenvectors, just immediately from how you multiply matrices. Right, because the first column of a matrix is the coefficients needed to do TV1, but if it's a diagonal matrix, then you only need that one coefficient, TV1 equals lambda 1v1. So it's just almost immediate from the definition that A implies B. Okay, and the rest I'll let you work through, but you should really treat them separately. Like, there's many proofs here. Then we have to prove that B implies C. There's actually even many ways to complete this proof. Like, we could prove that A implies B, implies C, implies D, and then we could show that D implies A, and that sort of completes the loop, and now they're all equivalent. So we don't even need to prove that that, for instance, D implies C, as long as we close the loop somewhere. Because why don't we need to prove that D implies C? Well, we do need to prove that, but if we prove this, that D implies A, well, we already proved A implies B, and we already proved B implies C, so therefore D implies C, because you just go around the chain. And I think what your book does is actually it completes the loop like this, and shows that D implies B, and I think also your book shows that B implies A. So your book actually does a tiny loop here and then a bigger loop here, and that shows that they're all equivalent. Okay. So give an example of a non-diagonalizable operator. So the one that I always, on a two-dimensional, okay. I always just go to this one. It's not diagonalizable. Because, well, you could prove it directly that there's not a second eigenvector with eigenvalue 0. So first of all, it's upper triangular, so its eigenvalues are 0 and 0. In other words, 0 is the eigenvector, or eigenvalue. V1, which would be the standard basis vector, is definitely an eigenvector with eigenvalue 0. But if you try to do like this one, it's not an eigenvector with eigenvalue 0. And I mean, the better way to think about this is what's the minimal polynomial here. So the minimal polynomial of this should be x minus 0. If it were diagonalizable, that would be the minimal polynomial. But in fact, so let's see, if we let P be, in other words, P of x equals x, and is that the minimal polynomial? Well, what would P of t be? Well, if P of x is x, then P of t is t, but t is non-zero. It's not the zero matrix, so this is not the minimal polynomial. In fact, the minimal polynomial, I think, is x squared. In other words, which I kind of think of as x minus 0 times x minus 0. Okay, because I'm thinking of 0 as a eigenvalue, but we have repeat factors in the minimal polynomial. And whenever you have repeat factors in the minimal polynomial, then you're not diagonalizable. And that's what that's a big theorem in this section. So, and you can see that t squared, if we do P of t, where P of x is x squared, that's t squared. Okay, what's t squared? Well, multiply this by itself, and you will get 0. Okay. So, right away by the theorem that we'll prove later in this chapter, or this section, this has repeated factors in its minimal polynomial, and therefore it's not diagonalizable. Okay. Let's look at 8. Prove that if t has dim v distinct eigenvalues, then t is diagonalizable. Well, if it has an eigenvalue, then that means there is a non-zero eigenvector. We know that eigenvectors with distinct eigenvalues are independent. And if we have dim v eigenvalues that are distinct, that means we have dim v eigenvectors that are independent. But that means they're a basis. They're independent and they have the right number dim v vectors. And so we have a basis of eigenvectors, which means that if we choose that basis, the matrix M of t is a diagonal matrix, and that means t is diagonalizable. Okay. Let's look at this one. So calculate t to the 100. So the only way we'd be able to do this is if these things right here are eigenvectors. And so let's just check that they are. I sort of trust that they are, but let's try 1, 3, 0. So if we do 1, 3, 0, we get, okay, I can do this, 5, 15, 0, which is in fact 5 times this thing. So 1, 3, 0 is an eigenvector with eigenvalue 5. Okay. So this one had eigenvalue 5. This one has eigenvalue 2. And what's 1, 6, 6? 2 plus 6 is 8. So it has probably eigenvalue 8. Okay, so t to the 100 of w is t to the 100 of, okay, these things added together. Let's call them v1, v2, v3. Or let's call them v2, v5, v8. So we just remember what the eigenvalues are. v2, v5, v8. And that just means we do t 100 times on v2, and then t 100 times on v5, and then t 100 times on v8. So the fact that we can really do this really quickly, this is going to be 2 to the 100 times v2. Because each time we apply t, a 2 pops out. The eigenvalue 2 pops out. Each time we apply t, the eigenvalue 5 pops out. And here we get the eigenvalue 8 pops out. And so that's the answer. We just take v2, the same vectors, v2, v5, v8, and we combine them with the eigenvalues to the 100th power, and that's, we've just done, that would be terrible to do if we didn't know these eigenvectors. So knowing the eigenvectors is very useful. This is kind of a simple application of that, but really you use eigenvectors to solve differential equations, to basically just simplify the problem that was unsolvable and make it solvable, whatever that problem is, and it can be many different things. Okay, find the minimal polynomial of this and explain why it's not diagonalizable. Again, we're going to use the main theorem that we haven't technically looked at in this video yet. But first of all, this is upper triangular, so the eigenvalues are 6 and 7. Now we're a little worried because there's 2 6s here. And we should be worried because I think what's going to happen is, well, you'd like, for this to be diagonalizable, we'd need the min poly to be x minus 6, x minus 7. Linear factors and no repeats. Okay, but if we do this, if we do t minus 6, t minus 7, let's do that. So, and really we're going to do actually m of t minus 6 times the m of identity, and then m of t minus 7 times m of identity. In other words, and we're just going to check, is this 0? Is it 0? And I don't think it will be. So that's going to mean that we're going to need a square here. So let's see if it's 0. If I take the matrix of t, which is up here in this basis, and I subtract 6 times the identity matrix, what I'm going to get is 0, 3, 4, 0, 2, 1. Okay, so that's this factor, t minus 6. And if I do the matrix of t minus 7 times the identity matrix, I'm going to get minus 1, 3, 4, minus 1, 2, 0. And now if I multiply these matrices together, I'm wondering, do I get the 0 matrix? And let's multiply these together. So if I take this, it means -1 the first column. Oh, so far so good. Maybe I will get the 0 matrix. Let's do the second column. 3 times this, minus 1 times... nope. Already I failed. All right, but let's just finish out 4 times, 2 times... yeah, so this is not 0. It's not the 0 matrix. So that means that this is not the minimal polynomial. And we know that the zeros of the minimal polynomial are the eigenvalues. We've proved that the zeros of the min poly are the eigenvalues. So like the min poly could only be this thing, or it could be, some power of x minus 6 and some power of x minus 7. We can't have any other factors because they have to be the eigenvalues, and we know the eigenvalues are 6 and 7. So like our min poly has to look like this. And what we've shown here is that we can't take this to be 1 and this to be 1. And so we're not going to be diagonalizable. What turns out to be the case is we get x minus 6 squared, x minus 7. That is the minimal polynomial. And it has a repeat factor, so it's not diagonalizable. But it is upper triangularizable. Well, of course, we had an upper triangular matrix. Okay, so that's number 11. Precisely state necessary and sufficient conditions to be diagonalizable over any field. The min poly over whatever field, the real numbers or the complex numbers, the min poly of t should factor into distinct linear factors. Should factor into distinct linear factors. Over the real numbers, you might even have quadratic factors. That would be a failure. If you have a quadratic factor, it's not going to be diagonalizable. Over the complex numbers, you can't have quadratic factors. It's always going to factor into linear factors, but you could have a linear factor multiple times. So not every operator will be diagonalizable, even over the complex numbers, because we could have these repeated roots. Okay. Prove that if T is diagonalizable and U is a subspace invariant under T, then restricting T to U is a diagonalizable operator again. Okay, well, let's use the theorem to prove this. So if T is diagonalizable, then the minimal polynomial of T factors into distinct linear factors. Okay, but when we restrict T to U, that just means we plug in only vectors in U, but vectors in U are also vectors in V. So that same minimal polynomial would be 0 on every vector in U as well, because U is a subspace of V. So the min poly of the whole operator on the whole vector space is also going to be 0 on every vector in U, but that means the min poly of T restricted to the subspace U divides the min poly of T on the whole space. But what does that mean? I mean, if T is diagonalizable, then the min poly looks like x minus 2, x minus 3, for distinct factors. So let's just pretend that it's x minus, let's say that there's just 3 factors. But how could a polynomial divide something that looks like this? Well, it has to be, either it's the same min polynomial, or it's just the first 2 factors, or it's just the second 2 factors, or it's just the first and third factor, or it's just one of the factors. But regardless, all these factors are distinct. So again, whatever factors appear here, which could be many different things, but in all the cases, they're going to be distinct linear factors. And so then, by the theorem, that means that this is diagonalizable too. Okay. So that's useful. Okay. Let's look at this one. This one's really fun. So, and to prove the result about factoring into linear factors, maybe I think it's just too much to do in a video. I'll do it in class. But let's just give the idea of the proof. So let's say if you are diagonalizable, then why does that imply that you have distinct linear factors? Well, if you're diagonalizable, you have a basis of eigenvectors. Okay, if you have a basis of eigenvectors, that means for each eigenvalue lambda k, t minus lambda k is 0 on that basis vector, the kth basis vector. And so because any vector in the space can be written as a linear combination of the basis vectors, then what happens is if you just string these all together, where you only count the distinct, so just nobody can stop you from forming this polynomial where you just put the distinct linear factors like this. Let's say there's k of them distinct. And if you let this eat v, it's going to linearly go through, and then you can reorder the factors so that you take the kth factor and put it first. Oh, this was a bad nomenclature. Let's call this lambda m. Take the kth factor in here, and then it's going to zero out that kth term. But there's many other terms here, like there's the v1 term. We'll just take this factor and move it forward when you act on the v1 term, and that'll put it to 0. And so it's 0 on a basis. That means this thing is 0 on the whole space. That means that this thing is the minimal polynomial. Now, the other direction is going to be the induction step, where say our minimal polynomial factors into distinct factors, where these are all distinct, why does that imply that the thing is diagonalizable? And so we need to find a basis of eigenvectors. That's the key proof. We assume that this is the min poly. We need to find a basis of eigenvectors. So the key, again, is to look at the range of t minus lambda m and also the null space of t minus lambda m. Okay. And right here, and then you're going to use induction on the number of distinct factors. If there's only one distinct factor, if your min poly is just x minus lambda 1, that's it. Well, then, this is the min poly. That means that's 0 on every vector. That means every single vector gets just scaled by lambda 1. So your operator is definitely diagonalizable. In fact, it's just lambda 1, lambda 1, lambda 1, all the way down until you fill out the dimension of the space. And so that's the base case, and then we use induction on the number of distinct factors here. And what we're going to do is we look here, and we'll see that actually you only need m minus 1 distinct factors to annihilate anything in this place, because this thing annihilated anything in the whole place. So on this invariant subspace, you have that just the first m minus 1 terms works, and so by induction then t restricted to this subspace range is diagonalizable. And so on this subspace range, we have a basis of eigenvectors. And all we need to do is then sort of string together and find, at the null space here, this is a subspace. Everything in it is a eigenvector of the eigenvalue lambda m. So nobody could stop us from choosing a basis here. But choosing a basis here is automatically of eigenvectors, because everything in here is an eigenvector except the 0 vector. Here, by induction, we get a basis of eigenvectors. And so the idea of the proof is to show that these two things, when you intersect them, are 0. Okay, and then essentially what you get is you get the whole space is a direct sum of this and this. And that's the idea. Okay. So maybe read the book's proof now, knowing sort of the general structure of how this goes. All right, let's do one more thing, this Gershgorin stuff. So, prove that each eigenvalue, lambda, is contained in some Gershgorin disk of T. So what's a Gershgorin disk? So once I think that's on the previous page, actually. Yeah, give a precise definition of the n Gershgorin disks with respect to a basis. Okay, so you get different Gershgorin disks for every different basis you choose. You can always choose a basis of the vector space and write down the matrix. Typically, this matrix will be horrible. It'll have all non-zero entries for a randomly chosen basis. In the best case, it's a diagonal matrix when we choose a basis of eigenvectors. But this is actually going to be, this Gershgorin disk thing is true for every single basis. You write down the matrix. And then what's the idea? So let's say our matrix was like 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have 3 Gershgorin disks in the complex plane. The first one is centered at 2. That's the center. And the radius of the disk is 7. Okay, so there's a big disk here centered at 2 of radius 7. And then the next Gershgorin disk is centered at 6. So it's the diagonal entries, 4, 5, 6. And it has radius, everything else in that row added up, so 5 plus 7 is 12. And you have to add up their absolute values, but I chose them all positive, so we get 12. So that's an even bigger disk. I don't know what it looks like. And then there's another Gershgorin disk that's centered at 10, way off the screen, and it has radius 17. And so you got these Gershgorin disks in the complex plane. This is the real part and the imaginary part, and this is the complex numbers. And your eigenvalues are somewhere in the complex numbers. Maybe they're a conjugate pair. Maybe there's a real one over here. But the point is that every single one of these is contained in at least one of the Gershgorin disks. So when you write down the matrix of a linear map error in any basis, you know where to look. You know where to look for the eigenvalues. Suppose you wanted to actually find the eigenvalues and solve a nonlinear equation numerically. This will help you know roughly where to start looking Like maybe you're going to use Newton iteration to find these zeros. And this will tell you where to look. So that's super useful to know sort of where to look in the complex plane for the eigenvalues. And this is true for any basis. Different basis, I get a different matrix, I get different Gershgorin disks, but in all the bases, these Gershgorin disks would, always contain the eigenvalues. So let's prove this. This is really fun. I really like this proof. So we have to prove that each eigenvalue is contained in some Gershgorin disk. So for some diagonal entry, we can create that little disk and it's in there. How are we going to prove this? This is so weird. Well, it comes from when you write something in a basis, the uniqueness of the coefficients is surprisingly how you prove this amazing result. That tells you where to look for eigenvalues. Okay, so say lambda is an eigenvalue. Well, then there's some non-zero v with tv equals lambda v, right? Now, v can be written in terms of the basis that you chose by some ci's, vi, okay? We chose some basis, and we wrote down the matrix of t in that basis. Let's call this matrix A. So it has entries, aij, and it's from this basis v1 through vn. These don't have to be eigenvectors. They can be any basis at all. This is so powerful. Okay. So what we're going to do is just replace v with the sum in the basis, and then replace v with the sum in the basis. And then we're going to, t is linear, so we can pull out the sum and pull out the coefficients. Multiplying by lambda is linear, so we can pull out the sum and do like this. Now here are the coefficients of vi. And then what's tvi? Well, by definition, tvi is going to be a linear combination of the basis with entries coming from the matrix. So it's the ith column of the matrix. So it's going to sum, let's say, sum over k of a k I v k. That's tvi. Okay? Matrix multiplication. This is the sum over I. This is the sum over I. And now what we're going to do here is we're just going to rename the index because we're going to collect terms of the of the kth factor over here. So we're just going to rename the summation index here as a sum over k of ck lambda times vk. And now let's collect the terms. Let's write this as a sum over k, and then collect all the terms which appear in front of the vector vk. And then over here we have a sum of vk, and we know this coefficient. So the coefficient of vk over here is ck lambda. The coefficient of vk over here is a sum over I, ci, a, k, I. Okay. All right, so we've expressed a vector, the same vector, in the same basis, and so because we have a basis, that means the coefficients have to be the same. There's only one way to write things, to write a vector as a linear combination of the basis. Each coefficient has to be the same. That means that we know that for all k, we can look at the coefficient of vk on both sides, and they have to be the same. For all k, the sum over I of ci aki is equal to ck lambda. Okay. And now, here's the clever thing. This is a sum over I, including when I equals k, so we'd have the akk component. So I'm just going to split that off. I'm going to have the sum over all the i's that aren't equal to k of ci aki, plus the term where I is equal to k, which would be ck akk. And that's equal to ck lambda. Now move this to the other side. We get a sum over the i's not equal to k of ci aki equals, and let's pull that ck out. We're going to get lambda minus akk. Okay. Now, at this point, I just want to point out to you, this is going to be the center. AKK, the diagonal entry, is the center of our disk. Okay? And what was the radius of our disk? Remember, I added up all the other entries in that same row. In the kth row, I added up all the other entries, not including the diagonal. and that's exactly this thing, except we have these bothersome coefficients that are unknown. Right, so when you choose a basis, you can write down M of t, and that means you know every single aij. These are the things we know. What we don't know is the eigenvector v, and we don't know how to write the eigenvector in our basis. So these CIs are unknown. We want to get rid of them. And this is the cleverness of the proof, is that, look, we want to get rid of these C's. So what we're going to do is, this is true for all k. Choose the index k. This is true for all k. Choose k so that ck is equal to the maximum over all the ci's absolute value. That means that if we take any other ci and divide by ck, this thing is less than or equal to 1. And that is going to allow us to get rid of all the c's. We're going to replace them with a less than or equal to something that completely gets rid of them and just replaces it with a 1. So that is going to be super useful. What we're going to do here is divide both sides by ck. So first choose k so that it's the maximum. That's why we're only going to get that each lambda is contained in some Gershgorin disk. Which one? It'll be the one that has the biggest coefficient. Which Gershgorin disk? It'll be the one whose diagonal entry has that basis vector, which when you write that eigenvector with eigenvalue lambda, which we don't know how to write and we don't even know what it is, but when you do write it, the coefficient will be biggest. That'll determine which Gershgorin disk it's inside of. And so we're going to divide, we got I not equal to k, ci divided by ck, aki equals lambda minus akk. And so now what we're going to do is we're going to say, look, the size of lambda minus akk is equal to the size of the sum I not equal to k, ci over ck, aki. But then by triangle inequality, do you know triangle inequality, like a plus b less than or equal to the absolute value of a plus the absolute value of b? So we're just going to do that to every term in this sum. Okay, and what that means is we can just say this is less than or equal to the sum now of all the ci over ck, aki. And the absolute value of a product is just the product of the absolute values. And this thing is less than or equal to 1 because nobody can stop me from choosing, we knew this for all k, so I'm just going to choose the one that has the biggest ck. But that means this is less than or equal to 1. So this less than or equal to came from triangle inequality. This less than or equal to is by my choice of k. I not equal to k, aki. And now I read this off. And what does it say? It says in the complex plane, the number lambda, its distance away from akk, the diagonal entry, is less than or equal to the absolute values of the other entries of the matrix in that same kth row. So that's how when I went over here and I looked, like, let's say I looked at the 6, that was k equals 2. It's the A22 entry. And so I went here and I put my center of the circle at 6, and now I know that lambda minus 6 is less than or equal to the sum over the I is not equal to k, so that's 5 and 7. So it would be the sum of this, which is, what, 12? So that's how I knew to draw a circle of radius 12 around the centers of 6. And I knew that every single eigenvalue has to appear in one of these disks. Okay. So I just think that's an incredible result. I think it's so cool. And it just shows you the power of mathematics that I didn't really realize, so I want to try to explain it to you. We have, in general, we don't know how to find the eigenvalues. You have to solve a nonlinear equation. We certainly don't know how to find the eigenvectors either. But we know that whatever basis we choose, we have this matrix. We know that there are coefficients. We just don't know what they are. Okay? But if we just give them a name, we just call them CI. We have no idea what it is. We give the eigenvector a name, V. We give this a name. And then we compute. And then we're able to, by cleverness, get rid of all the things that we didn't know about and just have things that we do know about, the entries of the matrix in whatever basis we chose. So that's an incredibly powerful result, that even if you don't know how to compute something or how to find something, give it a name and start computing with it abstractly. You might be able to discover something remarkable. That you can discover something about it without even knowing what it is. Precisely. So I really like this result. And additionally, you can prove that T is invertible. If this is called diagonally dominant. So if you're so lucky, you choose some basis, you write down the matrix of T, and it happens to be like 120, 2, 3, 17, negative 1, 2, and 14, 1, 1. The diagonal entries are so big that if you write down the Gershgorin disk, like here's the origin, we just want to show that 0 is not an eigenvalue. But if all your Gershgorin disks are over here, like the eigenvalues have to be inside here somewhere. So the eigenvalue cannot be 0. Right? So there's no eigenvalue 0. That means that the matrix is invertible. So if you want to show something's invertible, and you just choose a basis and you happen to notice that the diagonal entries are bigger than the off-diagonal entries, you might be able to prove that it's invertible using this sort of a trick, which I think is kind of fun. Okay, that's all for now.